Today, we will talk about the magnetic compass. This is one of the simplest, but also one of the most important instruments in an aircraft. And although it is not included in the 6 basic flight instruments, or 6-pack, that we have discussed in previous videos, it is closely related to the heading indicator. So, in simple terms, the magnetic compass is an instrument used to determine the orientation, or heading of the aircraft in relation to the Earth's magnetic north. To do so, the compass aligns itself with the lines of the Earth's magnetic field. Now, there are different designs and presentations of the compass, depending on its purpose. So in this video, we will deal with the most commonly used design in aircraft. But before going into detail with this, let's see what exactly is the Earth's magnetic field. The movement of molten iron in the planet's core induces the creation of a magnetic field around the Earth. So in other words, we could say that the Earth is a giant magnet. And just like a magnet, the Earth has 2 magnetic poles, north and south. This way, the magnetic field lines leave the planet at the South Pole and re-enter at the North Pole, as we can see in this example. Now, this magnetic field has several practical applications. For example, it protects the Earth from solar wind and excess cosmic radiation from space. It also allows the magnetic compasses to function, thus assisting navigation. But the question now is, how does a magnetic compass actually work? Or in other words, how does it use the magnetic field to work? Well, we have to say that in essence, a magnetic compass is basically a magnet that is free to rotate about a pivot point. As we can see in this example, the magnet is practically suspended in the air. It is only supported by a small pivot point around which it is free to rotate. Now, as the magnet is free to rotate, it will tend to align itself with the Earth's magnetic field lines. So if we put this system inside an aircraft, regardless of the aircraft's heading changes, the magnet will remain aligned with the magnetic north. In other words, the magnet acts as a magnetic north reference. The question now is, how can we take advantage of this to determine the aircraft's current heading? Well, to do this, we can add a card with the compass rose around the magnet in such a way that both move together. And apart from this, a heading indicator fixed to the fuselage is added. With this design, when the aircraft turns, the magnet and the compass card will remain aligned with the magnetic north, while the heading indicator turns with the aircraft. This way we can directly read the current heading in relation to the magnetic north. In this particular case, the aircraft's heading is 060. In this other position, the aircraft is heading east, or 090. And here, the heading is 330, and so on. Apparently, everything works fine with this system so far. However, there is a little problem that we have to address. The thing is that, normally the compass is located either on the top of the cockpit or above the instrument panel, like this. Inside we find the corresponding magnet and the compass card. Now, according to the design we saw earlier, the heading indicator would be located here, indicating in this case a north heading. The problem is that the heading indicator is not visible from the pilot's perspective. Therefore, in order for the pilot to be able to see the indicator, it must be located on the opposite side to its original position, like this. With this new design, a new problem arises. And it is that the compass indicates the opposite heading to the real one. For example, in this case, even though the aircraft is heading north, the compass indicates heading south. So, the solution for this is to invert the compass card so that the correct heading is indicated. Like this. Let's see how this new design would work. In this example, we can see the aircraft flying with a north heading, correctly indicated in the compass. Here, in the upper right corner is how the pilot would actually see the instrument. Let's suppose we execute a right turn to heading 030. And as we can see, it is correctly indicated in the compass. Here, another right turn to heading 060. And here we do a left turn to heading 330. So as we could see, with this design the heading indication is correct in all cases. However, there is a little effect that has to be taken into account. It is that the compass card will move in the opposite direction of the turn. Let's see an example. Here the aircraft is heading north. If it executes a right turn, for example to heading 030, the compass card will show an apparent turn to the left. We can see this effect again if we continue to turn right to heading 050. And if the aircraft turns left, the compass will show an apparent turn to the right. This happens because the compass card is inverted. And it is important for the pilot to be aware of this effect to avoid spatial disorientation and loss of situational awareness. Since under high workloads, or when there are not enough visual references, the pilot may believe that is making a turn to the opposite side. Now, another thing to consider when using the magnetic compass is that, since it is suspended over a small and sensitive pivot point, any turbulence, vibration, or maneuver may affect the heading indication or even make it impossible to read. That's why, in order to reduce this adverse effect, the inside of the compass is filled with liquid to dampen movements and thus obtain a more consistent indication. In most cases, the liquid used is pretty similar to kerosene. Now that we know the basic principle of operation of a magnetic compass, let's look at its parts. First of all, we have the main component of the instrument, which is the magnet, that remains aligned with the magnetic north. This is attached to a cup, which in turn attaches it to the pivot point. This pivot point is in contact with the compass card, and at the same time, all of these components are contained within a liquid-filled capsule. This capsule is transparent, and on the pilot's side it has a lubber line which indicates the current heading. And finally, all this is contained within an outer case. Now, obviously this design may have slight variations depending on the manufacturer and model, however the principle of operation remains the same. This is how we obtain the compass as we know it. Let's now see how to correctly read this instrument. Well, usually the compass card has reference lines spaced every 5 degrees. So that the long lines represent 10 degrees and the short lines 5 degrees. Here, the main cardinal directions are represented by their corresponding letters. And they are north, south, east, and west. Apart from this, every 30 degrees, a number which represents that heading is included in the compass card, omitting the last digit. For example, the number 6 represents heading 060. The number 12 represents heading 120. The number 24 represents heading 240, and so on. Now, the current heading is indicated by a lubber line on the instrument glass. For example, in this case, the compass indicates a north heading. Now, as previously mentioned, since the compass card is inverted, the headings displayed on it are also inverted. So for example, heading 030 would not be to the right of north, but to the left. In other words, the headings in the compass must be read from right to left. This may sound a bit confusing so far. So let's see a couple of examples. First, let's suppose the aircraft makes a right turn to heading 010. As we can see, heading 010 is displayed to the left of north in the compass card. In other words, we are counting degrees from right to left, starting from 0 degrees in the north. Now, if the aircraft continues to turn to the right, we can see this indication. If we are unaware, we might think that this represents heading 035. However, as we are counting degrees from right to left, this indication actually represents heading 025. In this order of ideas, if the aircraft now makes a left turn and the compass shows this indication, it represents heading 350. Now, some compasses incorporate an expansion diaphragm, which prevents damage or leakage from the pressure changes experienced by the liquid. And other components that can be found are, for example, the compensation screws. These is an adjustable screw system that allows the compass to be calibrated when servicing while on the ground. It should be clarified that these should not be adjusted by the pilot, as they should only be handled by maintenance personnel in an authorized workshop. Since the purpose of this system is to compensate for certain errors caused by compass deviation. Now, some designs also incorporate an instrument light for night operations, as well as a filler hole for the liquid. Having seen all this, we can say But the main advantage of the compass is that it does not depend on any other system to function. Because, unlike other instruments, it does not require electricity, air or vacuum pressure, or pitot static system information. Therefore, it is very useful as a backup or as an emergency system. This is why all aircraft must be equipped with a magnetic compass for both VFR and IFR flights. From the smallest and most basic aircraft to the largest airliners. Now, as we said previously, the compass indication isn't always completely correct. Since, as the compass has such a simple principle of operation, it has certain inherent errors in its design. Here we can mention the errors caused due to magnetic variation, compass deviation, and magnetic dip, which in turn can be divided into acceleration error and turning error. But we will deal with these errors in detail in the next videos. I hope the information presented in this video was useful. If so, don't forget to share, like, subscribe, and leave a comment down below. Thanks for watching.